10.2 Circular motion under gravity. Yes, we are back to circular motion. Due to gravitational attraction, many celestial objects such as the moon, the earth, or even the sun are performing their own circular motion. The moon is attracted by the earth. The gravitational attraction provides the centripetal force for the orbital motion of the moon, as in figure 10.2b. Mathematically, gmm over r square equals mv square over r, also equals m r omega square, which may allow us to calculate the orbital speed v or the angular velocity omega easily. By the way, the period t of the orbital motion is given by t equals 2 pi over omega. Example 6. Using the above formula, we may find the orbital speed v, the period t of the space laboratory easily. The orbital period is about 90 minutes. And yes, all low orbit satellites orbit the Earth about 16 times a day. And from the expressions, we can see that, first, the mass of the satellite does not matter. Second, the orbital speed decreases with distance r. Therefore, a satellite closer to the Earth's surface has higher orbital speed. Angular velocity also decreases with distance r, which means the period t increases with radius. The period of a satellite increases as the radius increases. Therefore, a satellite further away from the Earth has a lower orbital speed and longer period. Third, circular orbits must be around the center of the Earth. For other orbits, the direction of the gravitational attraction and that of the required centripetal force are different, which means the gravitational attraction will provide extra force that will pull the mass away from the desired orbit, and so the orbit becomes impossible unless the spacecraft has rockets to adjust its motion continuously. Fourth, to launch a satellite into a circular orbit, it should be given an initial velocity that equals the orbital speed in magnitude and tangent to the circular path, and at the right height. A satellite that starts from the right distance with the right speed in the right direction may carry on its motion just by the action of gravitational attraction, which provides the required centripetal force for the circular motion. Fifth, a satellite in a circular orbit does not speed up due to gravitational attraction, which is always perpendicular to the velocity of the satellite. Without air resistance, the mechanical energy of a satellite is conserved. Both its kinetic and potential energy do not change in an orbital motion. In example 7, the mass of the Sun is calculated. In example 8, the relationship between the period t and the radius r of a circular orbit is investigated. The relationship suggests that for two satellites of a satellite system, t squared over r cubed of the two satellites are equal. And this is similarly true for two planets in a solar system. For example, the period and radius of the Earth are 365 days and 1.5 times 10 to the power 11 meter respectively. The orbital radius of Mars is 2.28 times 10 to the power 11 meter, and the period of the revolution of Mars about the Sun. In example 9, we can find the orbital period of ISS, which is orbiting in a low-level orbit, and hence its period is about 90 minutes, similar to that in example 7. In part B, the weight of an astronaut is found to be smaller than that on the Earth's surface, as he is further away from the Earth's center. And what about his apparent weight? The apparent weight of a mass equals to the reaction on the mass. It is also the balance reading if the mass stands on a balance. Whether we are on the Earth's surface or in the space station, we are all orbiting in a circular motion. And so, gmm over r squared minus the reaction force N equals mv squared over r, or equals mr omega squared. So the apparent weight N, which is also the normal reaction, is always less than the actual weight mg. Binding moment equals to the centripetal force. In particular, for an astronaut orbiting the Earth in an orbit, his apparent weight is 0. He does not feel his weight, and we call this weightlessness. For the mass on the Earth's surface, as for question 30 in revision exercise, the centripetal force on the Earth, omega squared r, is largest on the equator and smallest at the poles. Therefore, the apparent weight N is smaller on the equator. Well, that means the balance reading is smaller if you weigh yourself in Singapore than that in Hong Kong. Exam link 1 investigates the motion of Jupiter's moons. The two moons have different orbital radii and hence experience different gravitational field strengths. Pay attention to part C. Exam link 2 makes use of the relationship between the angular velocity and orbital speed of a satellite of the Earth. The relationship suggests that v squared over omega equals the same constant for different satellites which orbit the Earth. Try checkpoint 4 below.